Few-shot learning, FSL, has gained popularity in machine learning communities due to its ability to rapidly generalize deep networks to new tasks with only a few annotated examples. However, most current FSL approaches work on 2D image domains, and its implication in 3D perception is relatively underexplored. 3D few-shot learning, 3D FSL, is more challenging due to unordered structures, high intra-class variances, and subtle inter-class differences. This work performs systematic and extensive studies of recent 2D FSL and 3D backbone networks for benchmarking few-shot point cloud classification. The authors suggest a strong baseline and learning architectures for 3D FSL and propose a novel plug-and-play component called Cross-Instance Adaptation (CIA) module to address the high intra-class variances and subtle interclass differences issues. The CIA module contains two modules: self-channel interaction (SI) and cross-instance fusion (SIF), which can be flexibly inserted into most current FSL algorithms with few changes and achieve significant performance improvement. The authors also introduce new splits of ModelNet and ShapeNet core, constructing two benchmark datasets, ModelNet40-FS and ShapeNet70-FS, for 3D few-shot point cloud classification. The problem definition and related work are discussed, where the goal of FSL is to train a predictor for query examples with few labeled support examples. Metalearning is the state-of-the-art paradigm, and the authors optimize the following objectives. Theta asterisk operator, phi asterisk operator equals argmin theta, phi L, t, theta, phi, 1. Where L, t, theta, phi, is the cross-entropy loss function defined as L, t, theta, phi, equals ET, minus log P, y equals C, x, 2. The prediction P, y equals C, x, can be given by P, y equals C, x, equals softmax, C theta, F phi, x, 3. The authors highlight the two key challenges in point cloud FSL: representing the point cloud data properly for few-shot learning and effectively transferring the knowledge gained in metatraining episodes to metatesting episodes with a small number of labeled samples with high intraclass variations and subtle interclass differences. The proposed method achieves state-of-the-art performance on the two newly built 3D FSL benchmark datasets, ModelNet40-FS and ShapeNet70-FS, under different settings. The contributions of this work include the first systematic study of 3D few-shot learning, proposing a strong baseline for 3D FSL, and introducing a novel plug-and-play cross-instance adaptation (CIA) module for 3D FSL. Here is a combined summary of pages 3 and 4 of the research paper. The authors review recent efforts in 3D point cloud classification and 2D few-shot learning. In 3D point cloud classification, deep learning-based methods can learn more complicated and representative features with deep networks. Existing methods can be divided into projection-based and point-based methods, with point-based methods such as PointNet, PointNet++, PointCNN, RSCNN, dense point, and DGCNN exploring local relations in a specific region to capture meaningful geometric features. However, these methods require a large amount of annotated data and may have poor generalization on novel classes. Few-shot learning is a promising direction for deep learning, with existing FSL algorithms based on a metalearning framework and categorized into metric-based methods and optimization-based methods. Metric-based methods focus on learning in embedding space where similar sample pairs are closer, while optimization-based methods regard metalearning as an optimization process. The authors perform an empirical study of different metalearning algorithms under few-shot point cloud classification tasks, using PointNet as the backbone for feature embeddings. The results show that metric-based methods outperform optimization-based methods in the point cloud scenario, with ProtoNet achieving top performance. The authors also study the influence of backbone architecture on few-shot learning, finding that graph-based networks such as DGCNN achieve higher classification accuracy. The authors identify challenges in 3D FSL, including strong intraclass variations and subtle interclass differences among the support set and query set, and propose a novel plug-and-play cross-instance adaptation (CIA) module to learn more discriminative representations. The CIA module can be inserted into existing backbones and learning frameworks to address these challenges. This research proposes a novel framework for 3D few-shot point cloud classification, addressing the challenges of subtle interclass differences and high intra-class variances. The framework consists of 3 modules: self-channel interaction, SI, cross-instance fusion, CIF, and cross-instance adaptation, CIA. The SI module models channel-wise relationships to learn more diverse features, addressing subtle interclass differences. It generates a query vector and a key vector from the embedding feature vector, computes a channel-wise relation score map, and reweights the initial feature to obtain a more discriminative feature. The updated feature is then combined with the initial feature to compensate for discarded information. The CIF module explores instance-wise interaction to address high intraclass variances. It concatenates each prototype feature with its top k cosine similar query features and vice versa, generating a weight matrix to update the prototype and query features. This process mitigates the distribution shift between the support and query sets. The CIA module combines the SI and CIF modules to learn more discriminative and diverse features. It updates the prototype and query features by feeding them into the SI and CIF modules, respectively. The updated features are then used to compute the probability of predicted labels using the square Euclidean distance metric function. The framework is trained end-to-end by minimizing the cross-entropy loss. The authors evaluate the effectiveness of the CIA module by comparing it with state-of-the-art few-shot learning algorithms on 2 3D point cloud classification datasets. They also conduct ablation studies to assess the contribution of each module to the overall performance. The results demonstrate the superiority of the proposed framework in addressing the challenges of 3D few-shot point cloud classification. Figure 2 illustrates the proposed framework, while Figures 3 and 4 provide visualization analysis of the SI and CIF modules, respectively. The TSNE comparison in Figure 3 shows that the CIA module effectively mitigates the distribution shift between the support and query sets. The accuracy comparison in Figure 3 demonstrates the improvement in performance achieved by the CIA module. This study investigates 3D few-shot learning, FSL, for point cloud classification, introducing a strong baseline using ProtoNet with DGCNN and a novel Cross-Instance Adaptation (CIA) module. The CIA module comprises a self-channel interaction (SI) module and a cross-instance fusion (CIF) module, which generate more discriminative features to alleviate high intraclass variance and subtle interclass differences between the support set and the query set. The authors construct 2 benchmarks, ModelNet40-FS and ShapeNet70-FS, for 3D point cloud classification, which are derived from standard datasets ModelNet40 and ShapeNet Core. The new splits ensure that the training and testing sets are disjunctive, meeting the requirement for the few-shot setting. Experimental results demonstrate the effectiveness of the proposed CIA module, which achieves significant performance improvement with different FSL algorithms and can be adapted well into different backbones. The ablation study in Table 6 shows that both the SI and CIF modules contribute positively to the performance of ProtoNet on ModelNet40-FS and ShapeNet70-FS. The network incorporating the CIF module achieves about 3% improvement for the one-shot setting. Comparisons with other 3D FSL methods in Table 7 indicate that the proposed baseline achieves much higher performance on both benchmarks. The feature visualization using TSNE in Figure 3 shows that the CIA module can mitigate the distribution shift between support and query sets, leading to better performance. The implementation details include using DGCNN as the embedding network, consisting of 4 edge conva layers and an MLP layer. The authors employ Atom Optimizer with an initial learning rate of 0.0008 and gamma of 0.5. And apply random points jittering and rotating to augment data during training. The results in Table 3 show that the proposed method exceeds other baselines by a large margin, about 5% for one-shot and 1.5% for 5-shot, and outperforms other baselines on both datasets. The comparisons in Table 4 and Table 5 demonstrate the generalization ability of the CIA module with multiple systems and backbones. The study provides a comprehensive analysis of 3D FSL, exploring the influence of different backbone architectures and proposing a strong baseline for benchmarking 3D FSL. The CIA module is a plug-and-play module that can be adapted into different FSL algorithms and backbones, making it a valuable contribution to the field of 3D FSL. This research paper presents a comprehensive review of existing literature on 3D point cloud processing, focusing on deep learning-based methods for classification, segmentation, and object recognition. The authors acknowledge the support of various funding agencies and institutions, highlighting the significance of this research area. The paper provides an extensive list of references, covering a wide range of topics, including few-shot learning, metalearning, graph neural networks, and convolutional neural networks, CNNs, for 3D point cloud processing. The authors draw upon the works of prominent researchers in the field, such as Charles R. Chi, Hao Su, and Leonidas J. Guibas, who have made significant contributions to the development of PointNet, PointNet++, and other 3D CNN architectures. The references also include papers on shape context, spin images, and other traditional methods for 3D object recognition, as well as more recent approaches, such as dynamic graph CNNs and spherical fractal convolutional neural networks. The authors highlight the importance of data augmentation, transfer learning, and domain adaptation in improving the performance of 3D point cloud processing models. Furthermore, the paper touches upon the concept of few-shot learning, where models are trained to recognize objects from a limited number of examples. The authors reference works on prototypical networks, relation networks, and other metalearning approaches that have shown promising results in this area. The paper also mentions the use of graph neural networks for 3D point cloud processing, which have been shown to be effective in capturing local and global geometric structures. The authors reference papers on PointGNN, SplatNet, and other graph-based architectures that have achieved state-of-the-art performance on various 3D point cloud benchmarks. Overall, this paper provides a thorough review of the existing literature on 3D point cloud processing, highlighting the key challenges, methodologies, and applications in this field. The author's comprehensive coverage of the topic will serve as a valuable resource for researchers and practitioners working in this area. This supplementary material provides additional details about the research paper on few-shot point cloud classification. It delves into the specifics of 3D backbone architectures, few-shot learning baselines, and the channel interaction module and cross-instance fusion module used in the proposed network. The paper employs three types of state-of-the-art 3D networks as support backbones for feature extraction: pointwise MLP networks, convolution networks, and graph-based network. For the pointwise MLP networks, PointNet and PointNet++ are used with modifications for simplicity and efficiency. The convolution networks include PointCNN, RSCNN, and dense point. For the graph-based network, DGCNN is utilized with edge conva layers to generate a 1024-dimension feature vector. In terms of few-shot learning baselines, metric-based methods such as ProtoNet, RelationNet, and FSLGNN are discussed. Optimization-based methods, including MetaLearner and MAML, are also introduced with their respective configurations. The paper also provides details about the channel interaction module, which is designed to enhance the representation of the input point cloud. The module uses two linear embedding functions to generate query and key vectors, and then computes a channel relation score map. This map is used to reweight the input features, and the reweighted features are combined with the original features to obtain updated features. The cross-instance fusion module is proposed to address the low data and high intra-class variances issues in few-shot point cloud classification. This module updates prototype features by fusing them with query features using a ModelNet40-FS. The updated prototype features are then used to update query features. The paper also presents additional experimental results, including fine-grained few-shot classification, ablation studies of residual design in the Psi module, comparison results of Morway K-shot settings, and the effects of CIA for 2D FSL. Here is a combined summary of pages 13 and 14 of the research paper. The authors present an ablation study on the effects of cross-instance fusion, CIF, and spatial channel interaction, Psi, modules in few-shot learning on point cloud classification tasks. The results show that the SIF module improves the performance of the ProtoNet model, especially in the one-shot setting, and achieves competitive results compared to state-of-the-art few-shot learning approaches. The Psi module is also shown to pay more attention to discriminative fine-grained parts of different classes, such as the cap of a bottle and the legs of a stool. The authors also conduct experiments on the ModelNet40-FS and ShapeNet70-FS datasets, which are new splits of the original ModelNet40 and ShapeNet core datasets, respectively. The results demonstrate the effectiveness of the proposed method in few-shot learning on point cloud classification tasks. Furthermore, the authors visualize the feature heat map of point cloud instances to qualitatively evaluate the proposed modules. The results show that the Psi module pays more attention to discriminative parts and structures, which enriches the information learned from point cloud instances. The paper also provides a dataset split for ModelNet40-FS and ShapeNet70-FS, including the number of classes, instances, and categories. The training and testing set splits are also listed in tables. Finally, the authors provide a list of references for the paper, including works on few-shot learning, metalearning, and point cloud processing. The research paper presents an innovative approach to enhancing the performance of point cloud classification models by introducing a novel module called Contextual Instance Attention, CIA. This module is designed to improve the feature extraction capabilities of these models, particularly in scenarios where objects are partially occluded or have varying scales. The authors demonstrate the effectiveness of their proposed CIA module through extensive experiments on various point cloud datasets. They compare the performance of their baseline model, ProtoNet, with its variants that incorporate the CIA module ProtoNet plus Psi, ProtoNet plus SIF, and ProtoNet plus CIA. In Figure 10, the authors provide a heat map visualization of point cloud instances before and after applying the CIA module. The deeper colors in the heat map indicate higher feature responses in specific regions, showcasing the enhanced feature extraction capabilities of the CIA module. The classes represented in this figure are bottle, airplane, and stool. Furthermore, the authors present additional heat map visualizations in Figure 11, comparing the performance of ProtoNet and ProtoNet plus CIA. The results clearly illustrate the improvement in feature extraction when the CIA module is incorporated into the model. The heat maps demonstrate that the CIA module helps in identifying and emphasizing the most relevant features within each point cloud instance, leading to better classification performance. The introduction of the CIA module addresses several limitations of existing point cloud classification models, such as their inability to effectively handle partial occlusion and scale variations. By leveraging contextual information from neighboring points, the CIA module enhances the model's ability to distinguish between different classes and improves overall classification accuracy. In conclusion, the proposed CIA module significantly enhances the performance of point cloud classification models by incorporating contextual information and attention mechanisms. The comprehensive evaluation and visualization provided in the paper highlight the potential of this approach in addressing challenges associated with partial occlusion and scale variations in point cloud data. Here is the combined summary. Figure 12 presents a heat map of point cloud instances, showcasing the feature response regions of two architectures, ProtoNet and ProtoNet with the confidence-aware initialization, CIA, module. The deeper color indicates higher feature responding in that region. Columns A and C display the results of ProtoNet, while columns B and D illustrate the results of ProtoNet with CIA. Comparing the two, the addition of CIA to ProtoNet results in more prominent feature response regions, as seen in columns B and D. This is likely due to the CIA module's ability to initialize the model with more accurate feature representations. The heat map also reveals that the ProtoNet plus CIA model produces more concentrated and robust feature responses, especially in regions with complex geometric structures. Mathematically, the CIA module can be represented as theta_0 equals phi, x_0, x_I, w. Where theta_0 represents the initialized feature embeddings, phi is a learnable function, x_0 and x_I are the input points, and w are the learnable weights. The authors hypothesize that the CIA module improves the robustness and accuracy of ProtoNet by incorporating the spatial information of point clouds into the initialization process. This is validated through experiments, as the ProtoNet plus CIA model outperforms the standard ProtoNet on several benchmarks. Notably, the CIA module does not introduce significant additional computational overhead, as demonstrated by the minimal increase in flops, floating point operations, in the experimental results. Furthermore, the heat map also illustrates that the ProtoNet plus CIA model exhibits more discriminative feature representations, which can be attributed to the improved initialization scheme provided by the CIA module. Overall, the incorporation of the CIA module into ProtoNet leads to improved performance and more robust feature representations.